Okay.
And so that should be good.
Okay, cool. So, everybody, welcome to Fluids Crash Course by me and a whole bunch of other random resources. So, first thing, what is a fluid? Basically, a liquid or gas. So, am I right in assuming this term is the mech stream of fluids? So, I did the civil stream, so we focus more on like liquids, so water, pipe flow, that sort of stuff. I think mech may possibly focus more on gas, so like air, like drag force, that sort of stuff. But same sort of fundamental concepts, so not really that deep. Okay, so important concept number one is that fluids deform continuously under an applied stress and they cannot withstand static shear stress. So shear stress is like a really important concept for the first part of this course. So yes, what is fluid? So then we get into fluid properties. So density, obviously a very important one. So density, I wrote the formula up here. So density is the Greek letter rho. So it's kind of like a curvy P. Make sure you make it abundantly clear that it's a curvy P and not a P, because P will be pressure. So make sure your rho is like rounded. And that is mass over volume with the units kilograms over meters cubed. So important value, density of water, easy number, 1,000. So kind of keep that locked away in your brain. Density of water is 1,000. So another fluid property is compressibility. So in this course, we treat fluids as incompressible. So you always would assume that, not that deep, just sort of keep that in your mind. There's the formula for compressibility. I don't remember ever actually having to use it, but I guess it's just good to know. Yeah. Okay, the next one is surface tension. So surface tension is pretty much, if you think about like a body of water, the way that the molecules are actually like sticking together, and tension would just, it's sigma, so it's work per unit area. Yeah. So here's sort of like more of a theoretical concept, I guess, is called capillary action. So if you look over here, you'll see with the water, we've got this curve here, right? It's curved upwards. But for the mercury, it's curved downwards. That's because the attraction for the water between the the attraction between the water and the glass is stronger than the attraction between the water molecules themselves. So the water grabs onto the glass. Whereas with the mercury, they're more attracted to each other. So they pull downwards and they create this little curve here, like a frown face. Yeah. So yeah, it's caused by the different surface tensions of the liquid and between the liquid and the solid surface. So you won't ever kind of really need to apply that, but it's an important concept to just sort of understand that different, like just because something's a liquid doesn't mean they're all going to be the same, act in the same sort of way. But you're mainly going to be dealing with water. We're not dealing with like mercury like flowing through pipes. So first sort of important concept with formulas you'll actually use is viscosity. So viscosity, the formal definition is that it's a measure of a fluid's resistance to flow. So the most common example would be water and honey, right? Both liquids, but if I pour water, it's just going to come straight out, right? But if I start to pour honey, it's going to fall at a slower rate, right? And that's pretty much because there's internal friction. And what I mean by internal friction is that within that section of liquid, the layers of the liquid, think about like the fact that honey is like sticky, right? The layers of honey are literally sticking to each other, right? So when they're falling, there's more friction, so it's happening at a slower rate. So, there are two different types of viscosity that you're gonna see. So the first one is dynamic viscosity, and you do need to know this formula. In this case, this formula's got it as, like, it's a Greek letter N, ni, but it can also be written as, like, mu. So depending on, I think on your formula sheet it's mu, but don't be thrown if you see that it's the same thing. So dynamic viscosity, is shear stress, so the tau over du dy. And then we've got kinematic viscosity, which is the dynamic viscosity over the density. So they're not particularly like difficult formulas, but you do need to know them. So okay, so before I talk about the 3 different types of flow, I'm just going to talk a bit more about the viscosities. So let's say I've got a rectangle like this. Can everybody see that, or should I write it somewhere else? Everyone okay?
Yeah.
You can see it? Okay. So let's say we have that, and there's a shear force, right? So a force along that side. It's going to theoretically deform something like this. Right? So our dy is obviously going to be this length here, and our du is going to be there. And in terms of flow, acting that way. So u is the velocity of the flow, and this will be our force. Does that sort of make sense? It's not, it's like pretty chill. Okay. So you can have different sort of scenarios. You can have, like, pretend this is like a fixed plate up the top here, a fixed plate down the bottom here, or maybe just a plate in the middle. There are a couple different scenarios you can get, but overall it's not particularly difficult. So now there are 3 different types of fluid flow. So they are laminar, transitional, and turbulent. So the 2 most important ones are laminar and turbulent. Transitional is a bit weird. It's like a very sort of small section of, like, in terms of like smooth flow to turbulent, if it's like a range, it's quite a small middle section, and the math for it is really complicated because at like what point is it really transitional and whatever else. So you won't get a question on that, but it's important to know that like there does exist a middle between laminar and turbulent. So laminar flow is this one over here. So you can see the water smooth, flowing in one direction. There's no mixing. So that's just like, kind of like, you know, water, if you open your tap, flows one direction, smooth, normal water. Then you've got turbulent flow, which would be like whitewash in the ocean, yeah? You can see it kind of curls in, there's mixing, it's all chaotic. Every single particle in that is acting differently. So one of like the key, you'll learn this at some point, I think it's later in the term, is that we can't properly model turbulent flow like on a computer because every single particle acts differently. Like there's no formula for that, right? So that's why a lot of the math that we do is kind of to do with turbulent flow, and we sort of generalize it. But it's very chaotic, a lot of swirls, and it's got eddies. So eddies are backflow. So if you see up here, what kind of happens is it like accumulates, right? Because what's happening is the flow is going that way, but then there's like forces coming back and it's pushing them backwards. So there's like a backwards curl, and then there's like these weird sort of circular back swells, and they create this accumulation of fluid. So that's an eddy. As opposed to the laminar flow, we don't have any of that. There's no accumulation, yeah? It's straight through, smooth, all good. Cool. So, and lots of, one of the other key differences, yeah, it's laminar flow, no mixing, turbulent flow, a lot of mixing. Okay, here is a very important concept. It's called the Reynolds number. It is pretty much a ratio of inertial forces to viscous forces. That's the theory behind it. What we actually use it for in this course is to determine whether our flow is laminar or turbulent. Now, if you Google it, there's a couple different values for when something would be considered like smooth, turbulent, or like all these different ones. General gist is that if it's below 2000, if your Reynolds number is below 2000, it's laminar. Somewhere above 4000, it'll be turbulent. In your exams, it'll be like shockingly obvious which one it is. They're not going to give you something in the middle. It'll be like 1,000 or 500,000. So don't worry about you'll know which one it is. It's not they won't make it like iffy for you. So how do we calculate it? It's this formula over here. So it's fluid density times by flow velocity times by something called characteristic length. So I'll explain that a bit later, and over your dynamic viscosity. So that is how we calculate Reynolds number. Characteristic length, that depends on what shape you're talking about. So if you're talking about a pipe, it's your diameter. If you're talking about a sphere, it's also your diameter. If you're talking about a plate, it's the distance from the front edge. So what I mean by that is if we have a plate like this, and there's flow this way, our characteristic length would be this, because this is the front. Does that make sense? Cool. So, yeah, that's the formula. You will definitely need to know that. Be good at calculating it and identifying which flow we're talking about. But again, they usually make it shockingly obvious which one. So, this is, we already did this. Newton's law of viscosity. The slide is in the wrong order. Doesn't matter. Here's a good diagram. Sure. So, we have a plate on top of this water here, and there's a force. So, our shear stress is going to act sort of in this triangle here, right? As closer it is to the plate itself, the more that the water is going to be shifting, right? As opposed to the water like way down below. So this is sort of what your diagrams will tend to be looking like, and it's a bit weird. This is like a front-on view, but you also got to think about the depth sometimes as well. So one of the hardest things that I found in this course was being able to visualize those and reading the questions and doing the diagrams. So I highly recommend that in all your tutorials, you practice drawing out the diagrams, because you will get them wrong a lot of the time in the beginning. And they don't have to give you the diagram in the exam. And if you don't have the diagram, then it makes the question like really hard. So very much practice drawing this out and understanding, okay, if I'm drawing the front view, then I still got to think about what my depth is and all of that sort of stuff. Okay. So, pressure. Pressure is obviously very important when we're talking about water specifically. Water pressure, so average pressure, easy, force over area, we all know this. Now, this is where, so we have absolute pressure and what's called gauge pressure. So that's like from some sort of measuring device. Now, don't write REL, write gauge, like G for gauge. So absolute pressure is the gauge pressure plus the atmospheric pressure, which is 101.3 kilopascals. So you have to be really careful in the question whether they're asking for absolute pressure or gauge pressure, because they can ask for both, and they can like try and sort of trip you up. So there's a couple of different measurements of pressure. So we've got what's called a piezometer and a simple manometer. So a piezometer looks something like, kind of looks like a weird thermometer almost, like you'll see a circle, this with a center. Also, just a weird side note for this course, kind of get used to thinking about things in terms of diameter and not radius. So think about area as like pi d squared on 4. It just, I don't know why, it just happens. So don't mess it up. Oh yeah, so piezometer, and then maybe you've got like another sort of pipe coming out this way here. So that's a piezometer. The spelling might be incorrect. And then you've also got what's called a manometer, which is kind of like a bit more funky, but not too much. It's like, tends to be like this, and then maybe the pipe goes down and like back up or something like that. So that's like a manometer. So they both measure pressure, and important concept, they measure pressure, you assume that it's like in the middle or like in the center, if that sort of makes sense. Like so here and here. So let's say we have I'm going to draw this one a bit better. Let's say we have something that goes like that, and then curls back around. Okay, that's a kind of janky drawing, but you see what I mean, yeah? So this is A and this is B, okay? So let's say we want to measure the pressure, like A or B, yeah? So let's relate the pressure in A to the pressure in B. So what you can assume is the pressure across any height like that, well, that line's kind of diagonal, but assume it's straight, is going to be the same. So if you find the pressure up here, you then jump to this point over here. Does that make sense? So you find the pressure, because pressure, when you're talking about liquids, let's say you have a bath, right? And you push a block of something down. And let's say I push a block of something down 2 meters to the right in the same bath. Same pressure, right? Because it's to do with the water above and below. So, yeah. Okay. You can also have different liquids within one of these scenarios. So let's say you've got water from here to here, and then from here to here you've got mercury. So the way you would do this one is you would say they would give you the height from here to here. Let's say that's H1, then this is H2, and this is H3, so to the center. Always beginning and ending at the center. So the pressure at B, oopsie doodles, would be calculated. So if you want B, then you start at A. So if I've gone from somewhere down here up, do you think my pressure's like increased or decreased if I've come further up? Yes, exactly, right? So that means we're going to have minus, what the way the formula goes is, so yeah, it'd be minus gamma times H1. Oh, did I talk about gamma? Oh, my bad. Gamma is this thing called unit weight. So it's weight, so I'll write it over here. Gamma is equal to density times gravity. My bad. So that's another fluid property. So unit weight, density times gravity. The way you derive this, you would say weight force over volume. Weight force is mg, volume is meters cubed, and you'd get this. Super important formula. My bad, forgot that one. Gamma equals density times gravity. So, to find pressure, you would start at your middle. We're going up, so we're losing pressure. So it's minus gamma H1, and we go up to where this liquid would be. So we go from here to here, and we can jump straight to this point here. And then we're going to go from here. We want to find out, we can jump across again. But now we've got to find for this different liquid, right? So because this, if we break this down, you'd get density of the water times gravity times H1, right? But this mercury is going to have a different density. So you've got to calculate it separately. So you'd go again, minus the density of the mercury times gravity times H2. And then from here, we can jump across to here. And if I'm going from here down to the center, I've gone down, so I plus. So I'd be plus density of water times gravity times H3. So, yeah?
Sorry, I was just wondering, can you jump across from the mercury to the water? Is it from H?
You can, yes.
H2 to the, yeah.
You can jump across at, because technically you can jump across at a boundary. So I can go from here, from this boundary here, across to here.
Even though the liquid changes?
Yes, you can do that. I know it sounds a bit illegal, but like you can do it, so just like enjoy it, I guess. Is that okay? So main concept here is the plus or minusing. Think about it, okay, I'm going down, so my pressure is increasing, so I've got to add pressure. I'm going up, I'm losing pressure. Oh, yeah, cool? Okay. So, here's an example that I got from the textbook. So this is a classic example, very similar to this one just here. So, we've got A, we've got B. Determine the difference in pressure between the centerline points. They don't need to tell you centerline points, you'd always just assume that, okay? So, we go, oh, and they've given you the densities and sort of whatever else. Also, assume liquids are incompressible. That's for this whole course. Okay, so you don't need to write that down, but like just kind of know that that's what you're doing. You're assuming that they're incompressible. So we're going to start at this one from point B and move our way through the manometer. So the pressure at B, we're going to go from B all the way up to this boundary here, where with the where the mercury is gonna, where we can jump across to the mercury. So point B, we've gone up, so we've minus the density times gravity times that height. Okay, then we jump across from here to here, and we're going to go down to the next boundary, which would be here. So we jump, so we go here. We've gone down, so we're increasing pressure, so we add, and we've got mercury. So it'd be a different density times gravity times that height. So we're here now. We can jump across. Then from here, so from here, we can just go across to here and go down. So we add the final water pressure. So that's how you get an equation like that. And then you just substitute all your values in. Make sure everything's in the same units, especially the densities. Like sometimes it can be a bit mean and give you one in one like grams and not one in kilograms. Just make sure that everything's in the right units, because you're kind of going to get, it's hard to do a sense check with these questions because the numbers can vary so much depending on the liquid, depending on all these other things. So make sure you sub everything in correctly. And then if we've got P, all these numbers A, to find the difference, we would just minus them onto the same side. Is that all okay? This is a very easy concept that gives you good marks in your exam. And also the final for this is like closed book. Is it closed book for you guys? Maybe it's open book. Mine was closed book. Do you know? I think it was maybe open book. But anyway, like this sort of manometer question, this is as hard as it's going to get. So if you're really good at it, then it can be like 15 marks in your exam. So I would say heavily practice that one. Okay. So I don't know where hydrostatics is taught in you guys' course, but for ours it's somewhere near the beginning. So what hydrostatics pretty much means is if something's under the water and it's like still and it's just like low-key staying there. So it's called hydrostatics. You can also hear terms like forces on a submerged body. So just think about if you had a ball in the ocean and you pushed it down and you like stayed there, what's happening, what are the water pressures, what's the forces, all that sort of stuff. So when we're talking about hydrostatics, there are sort of three important things that you're usually going to need to calculate. Very important formulas. First thing, the resultant force from the water pressure. So when something is being pushed under the water, there is pressure from the water, right? So that is our unit weight times by H. So sometimes it's big H, sometimes it's like H bar, like a H with a little line on top. That pretty much means just the height, how far down it is, and then the surface area. So then we also want to usually know where on our submerged body is this force actually occurring, right? So we need to find the X and Y coordinate. This formula looks tricky, but it's kind of not too bad. So it's the distance Y, so the Y distance, plus moment of inertia over that Y distance times A. And then usually they are only going to ask you for the Y coordinate. They can still theoretically ask you to find the X one, but I don't know, it's kind of more rare. They more care like vertically on that submerged body where that resultant force is happening, or the center of pressure. So if they ask for center of pressure, you've got to know to find these two coordinates. Sometimes they ask for X, sometimes they ask for Y. Depends on what sort of submerged body you're dealing with. So I'm going to draw up another example. So let's say also you're going to see there's sort of some like diagram things you should know. This little triangle indicates like water and like the top of the surface water. So you've got to know that. So let's assume we have this wall and there's water all the way here. Okay? So if we want to find the hydrostatic force, we've got to think about how our pressure or force increases as we go down. So if we draw that visually, that's going to look like this. It's going to be a triangle. And that makes sense, right? Because up the top, up kind of little to no force or pressure, as we go down, it's going to increase like linearly, I guess. So usually let's assume this is, I don't know, a floodgate, could be some sort of dam, wall, sort of a thing, all of that. So if we want to find the hydrostatic force on something simple like this, it'd be force is equal to, we think about this triangle here. So it'd be half times by the pressure here would be, it's the gamma times h, right? So that would be rho g h. So it's half rho g h times by height, h. Yeah? So I don't know if you get that formula in your like formula sheet or whatever else, but you can just derive it by looking at that like force diagram, I guess. So that is the area of this triangle here, right? But again, we're thinking about this is a front on image, right? This is me looking at the floodgate, but there is like a depth to this, right? So you've also got to times that by your B. Like you're going in. Does that make sense? So this is like what's it called? A cross section. A cross section, and you've got to think, okay, but that's occurring for all of the wall. So we've got to times it by our breadth all the way back. Is that okay? Cool. So the second kind of submerged force you could get is a really mean one is like a curved one. That's kind of harsh. I don't think you do learn about it, but like to get it in an exam I think would be kind of mean, but you never know. Sometimes they're mean like that. Another one is an inclined wall. So we just did a vertical one, which was pretty chill and easy. But what about if we had a wall that went like this? At an angle of theta. Yeah? So, again, this is our water. Sometimes I draw a little line thingy underneath it. So, this is where the distinction between the height and then the height of the pressure becomes important, okay? So, this water goes from here. Let's assume like that. Okie dokie. So, find the hydrostatic force. So, we said hydrostatic force was force times gamma times h times A. But what is that h? What you're gonna think is that it's this. Bum bum, that would be wrong. What it actually is from the top to the center of that wall, okay? Because it's on, so when we did the flat wall, the straight wall, that h, if we had a wall here, the center of pressure is the same as the whole height, right? But on an incline, that's not necessarily true. So we have to do a little bit of year 8 soccer toe trig to find that. So if we have the formula, F is equal to gamma H. Sometimes it's HC, sometimes it's H bar, sometimes it's big H. Up to you kind of what you want to label it. So that's so, and that will do for this one HC. So let's assume this is H, this height. So I like to use HC because it's like the height to the center. And then you've also got this YC. So that kind of inclined distance to the center. And we can relate these using, like I said, year 8 trig and say that HC is going to be YC sine theta. So then our force would be gamma YC sine theta A. And when you're talking about A, it's not like this kind of section of the wall, it's the wall all the way in. So if it was a square or rectangle wall, it'd be this length here times by the breadth, so looking in. Does that make sense? So a lot of people get confused, like they miss that. You got to think about the area. This is a wall that's being cut all the way in. So it's this times by that breadth backwards. This is probably the hardest topic conceptually in the whole course. It's a bit weird, but once it kind of clicks and the diagrams, once you understand the diagrams, you are so fine. So practice a lot for like understanding these diagrams. So if we wanted to find this theoretical point, center of pressure, point of application, there's a couple of words for it, we would then use these two formulas here, with this x and y, this big x and y being the HC and the YC. So the center on this where that pressure is acting. Cool? Also, they're going to give you all of the like, for like IXX and IXY, they'll give you all the formulas for that. So you don't think you need to memorize them for like all the different types of shapes. They'll give it to you. So yeah, the last one is if they give you a curved surface. So that would look something like, like this almost. Very mean. Math is kind of hard. You'll go through it in your tutorials. It's kind of not that important though. Like mainly the inclined plane is the one that they like to test because it's harder than just the basic straight floodgate, but it's also not the curved one. I low-key don't remember how to do the curved one, sorry, but you're kind of on your own for that one. Okay. So, the next important topic is something called continuity. Continuity sounds way fancier than what it actually is. All it means is what goes into the pipe comes out of the pipe. Crazy, absolutely insane. So, let's say I have a pipe. Also, pipe flow is so much fun, guys. It's like the best topic. Leo, do you agree?
Yeah.
It's good.
It is fun.
It's fun. Okay, so pipe. They demonstrate pipes like this, okay? Don't expect to see anything circular. Don't draw any circular pipe diagram because it's just wrong. Sometimes I've got like a weird squiggly line like that to kind of show the beginning and end. So there's also, there's a thing, so continuity. I low-key forgot to put a slide on this. I don't know why it's so important. Continuity. I think that's how you spell it. So what goes into the pipe comes out of the pipe. So there's this thing, you're going to learn about it. It's called Q. Q is your flow, okay? So, flow. And the formula for it is velocity times area. And that makes sense, right? Like theoretically. How fast the flow is going multiplied by how much space it has to go through, right? Would be how much flow we've got. So flow rate. So this, let's say we have a Q1 here and it's equal to 10, for example. Q2 would be shocking 10 because 10 has gone in, 10 must come out, okay? And so very sort of common basic question would be something like, so yeah, we have a flow rate of 10, we have a velocity of, I don't know, 2 meters per second, a diameter of, I don't even know, whatever. So if things are the same diameter, you're gonna have the same flow rate, okay? Q1 is gonna equal Q2, but let's think about, what if I had a pipe that went like this and then decreased and went like this? That flow rate is not going to be the same because I've now got a much smaller surface area. So the rate at which the water can flow out is going to be different, right? So I'm going to make up a question here, so just like bear with me for 1 second. So let's say Q1, actually no, I'm not going to give you Q. Let's say we have a velocity flow of 10 meters per second. We have this diameter of 0.5 meters, and it reduces to a diameter of 0.1 meters. And we want to find our output flow, so our Q2. The math is really easy. Just like use your brain. Q1, we can calculate. It would be U times A. So it would be the 10 meters per second times by area. What we mean by area is cross-sectional area. So that would be pi 0.5 squared over 4. Okay? Then what's gone in has still got to come out. So this whole thing, I don't have my calculator on me, but it's going to be equal to Q2. So I'm just going to call this number like M for Maria, okay? So let's assume that's M. Our Q2, we want to find the velocity, so it would be U2 times A. A we can rewrite as pi times 0.1 squared over 4, and then we can solve for U. So very common type of question where they've said like, oh, flow goes in, but the diameter has been reduced to blah. What would your new velocity be? And then you would say Q1 is equal to Q2, U1, A1, U2, A2, blah, 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 do all your calculations. Pretty chill, right? But just remember, if it's the same pipe, like same diameter in and out, flow rate's the same, doesn't change. Cool? Cool. Oh, okay. Here's like a bit of a theoretical thing. I forgot to put in the slides. There's something called a control volume. Pretty much, it's just like what you've determined to like the volume that you're looking at. So in this case, your control volume would be like this whole thing here. I don't know. It's kind of useless concept, but whatever. Okay. Here's a good example of a hydrostatic. So, let's say we've got this weird little bucket thing and we fill it with water. This is on an inclined angle, right? This was like, I wiped it off. It was like the inclined angle example. So, what they would normally, they would give you this and you'd have to draw your diagram, okay? So, that's a bit hard. Let's try. So, you've got to draw it from this front plate's perspective. That's how you draw the diagram. So, the way you would actually draw this is you would draw, first of all, that like incline. So this line here is this line here, right? Then you would say the pressure is acting, what's that distance? 3. So this here is 3, right? And we've got the pressure acting like this. It's like a triangle. Right? So they'd probably ask you like, what's the this question's asking the force of the water. So you would take this would be your big Y, but your YC would be from here to the midpoint of that, yeah? So that's your YC. Your HC would be here to that point here. Does that sort of make sense? So you take that front section of the diagram, you kind of rotate it, and that's what you draw. And that would be the correct diagram. And then you would then have to also remember about the breadth. So then that's like, you don't need to draw that on your diagram, but when you're calculating your area, that would be like an important concept. Is that okay? So that diagram's good to kind of show you like when it looks like when it has that breadth. It always has it, but like usually you don't really get to like see it, I guess. Okay, here's like a random concept that sometimes gets assessed and sometimes doesn't. It's called buoyancy. Pretty much, I can't remember which scientists like did this, but allegedly what happened was some dude sat in a bathtub and was like, crazy, when I go in the bathtub, the water goes up. Why does that happen? My volume has displaced a certain amount of volume within that bathtub, right? So kind of like how like big ships or like glaciers stand, right? Like why don't they just sink? Because there's actually something called the buoyant force holding it up. And the way you calculate it is its force is equal to density of the fluid times, now this V, this volume that they're talking about, is not the volume of the whole object. So let's say I have water like this, and I've got like, I don't know, a weird sort of circular thing. Actually, that's dumb. Let's make it a rectangle. A rectangle here. That's half in, half out. The volume would just be the half that's under the water. It's the displaced volume. It's not the volume of the whole object. If the whole object is underneath the water, then yes, it would be that volume. But if it's partially in, partially out, it would just be the displaced water volume times by gravity. Does that make sense? Okay, so yeah, the principle is that when a body is placed in a static fluid, so it changes obviously if you've got like flow and all of that, but that's why bathtub is usually the best example. It's buoyed up by a force equal to the weight of the fluid that is being displaced. So we would have force of gravity going down, but we'd have the buoyant force going up. And that's what's actually sort of keeping it afloat. Does that make sense? So big concept here is don't get the V mixed up. I know I keep saying it, but it's because everyone does that. It's the volume of what is underneath the water, not the entire object. Yeah, sometimes it gets assessed, sometimes it doesn't. Kind of like just sort of depends, I guess. Okay, here is personally what I think is the most important part of the course. So, my favorite equation in the whole entire universe, the Bernoulli equation. Such a beautiful, sexy looking equation. So, it's pressure. Why are you shaking your head? Do you not agree, Kaden? It's actually like it's the best equation, guys. Oh my god, I'm obsessed. So, So the Bernoulli equation is somewhat special because in this case, we assume that there's no energy loss through the pipe. But think about it, like if water's going through a pipe, there is energy loss, right? There's going to be friction between the pipe and the water. When it's like entering and exiting a pipe, there's like loss there, all these different things. But such a beautiful, crazy, sexy looking equation. It's also equal to some sort of constant. Sometimes it's usually written as head loss. So it'd be like P plus whatever, blah, 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 is equal to like H. You might see it written like that. And that is referring to total head, total head. And that's, so it's just equal to some sort of constant, I guess. Hello, Red. So, the way that you can kind of write the equation in different ways because there are obviously sort of like equivalent stuff, but the way I liked it the best was, I'll write it here, P over, so P, this is pressure. Again, this is where writing clearly what your density and your pressure is important because they're in this same formula. So it's pressure over density times gravity plus U squared over 2 times gravity plus Z is equal to H. That's, in my opinion, the best form. Some people write like the density times gravity as gamma, but I think it's easier to just write it out in full. This equation is now your life. It's your best friend. Make it your screensaver. It's the best equation in the whole wide world. Okay, so pressure, so that's why, yeah, make sure you don't get your P and your density mixed up. P at the top is pressure, the rho down the bottom is density. Okay, what is the Z? The Z is the height from sort of what you've determined to be your zero. There's an official word for it. What's the word for the
Datum.
datum? That's it. Thank you. So height. So Z is your height from datum, and you pick where your datum is. Normally it's like really obvious where you would put it at the bottom. Be weird to put it at the top and then make your numbers negative. But technically, if you put it, you can put it anywhere you want, and as long as you keep it consistent through your whole question, you'll get it right. So that is the Bernoulli equation. So awesome, so beautiful. So there's these things called head. To be completely honest, I never really understood what they meant by head, but I can tell you what they are. This section here with the P is your pressure head. Again, don't ask me what they mean by head, I never fully got it, but I guess it's just sort of a concept. So pressure head, this is your velocity head, and this is your elevation head. So if you have your pressure head plus your velocity head plus your elevation head, that equals total head. How exciting. Very strange. I don't know why it's called head, but that's such is life. I don't know. Okay, so yes, this one assumes no energy loss. So this is a really good example. Water flows through a pipe at A, which is the one at the top, at 6 meters per second. Determine the pressure at A and the velocity of the water, and its exit at B. So we're going to use the Bernoulli equation. So what you would do is, you would say, I always wrote out the full equation. So also the total head at A is going to be equivalent to the total head at B. So you would have the pressure at A over density times gravity plus the velocity at A squared over 2g plus ZA is equal to the pressure at B over density times gravity plus the velocity at B squared over 2g plus ZB. Write out the full thing like that, okay? Then sub in what you know. So we want to find pressure at A. Well, we know density and gravity, right? We know the velocity at A. We know this. So our ZA, I'm going to make my datum this line here, and assume your datum goes through the middle of the pipe. Always assume middle of the pipe. So my datum's here. My ZA would be 3. So let's sub all that in. You'd get PA over 1000 times 9.81 plus 6 squared over 2 times 9.81 plus 3 is equal to, now, fundamental concept here, pressure at B. It's exposed to the atmosphere, so it's 0. Okay? If you're, more often than not, if you're looking at a question, you're like, where's my pressure for this one? What the hell? It's not in the question. I can't figure it out. Think, is it exposed to the air? It's 0. So that all becomes 0. How much fun is that? So much fun. So if it's like a hose being shot up, if it's water flowing out of a dam, if it's water flowing out of a pipe, as soon as it's exposed to air like that, the pressure is 0. So then what about our velocity at B? Well, we've got a pipe. Does the diameter change? No. So our velocity is going to be the same. So we can write that as well as 6 squared over 2 times 9.81. And if you did your whole continuity thing and you went QA is equal to QB, and you said UA, so that's 6 times by pi times d squared on 4 is equal to UB times pi d squared on 4, you'd be like, oh, lol, like they're all the same. It's the same diameter, so our UB is going to be 6. Yeah? So you can go through, like, if you're unsure and you're like, oh, is that do the same blah blah, that's fine. Just use your continuity to kind of like double check yourself, I guess. But then you'd find that, yeah, UB is 6 squared plus now our ZB. I put my datum at B. So therefore, my elevation from that is nothing, right? So it's 0. Then these cancel. So I can rewrite my equation as PA over 1000 times 9.81 is equal to minus 3. Pressure at A is equal to minus 3 times 1000 times 9.81 Pascal. Cool? So, very important stuff. Bernoulli equation, write this full thing out. I hate to tell you this, but you're not a genius. So you're not going to sub it in right unless you write it out properly. So don't skip to this. You're going to get it wrong. Take the time to write out the full equation and sub everything in properly, and you will get it 100% right every time. Cool. So that is a special type of question because we assume that there's no loss. We assume that there's no friction between the water and the pipe. We assume that there's no like extra loss at the entry or the exit point. So unfortunately, life is not like that. So this is actually the full equation, such a plot twist. So same thing, except you add on this thing, HL. That stands for head loss. So it'll be written as usually like HL, sometimes big HL, kind of like doesn't really matter that much. So let me just triple check I've gotten the friction formula. So what makes up your head loss is a couple of things. It's your friction and your entry and exit. Those are the three, so entry, exit, and any like janky movements in the pipe. And what I mean by janky movements is if your pipe goes like janky movement, yeah? Weird, not nice, would create extra energy loss. So, sorry guys, I forgot the formula for that, one moment. So all of these things add up to your head loss. Also, we also have these things called pumps and I think turbines. So if you get a system that includes a pump or a turbine, a pump is easy, pumps energy into the system. Turbine takes energy out of the system. So you would put your pump on your original side and your turbine on the side with your head loss because it's taking energy out. Head loss is taking energy out. But low-key, I don't remember that coming up in the exam, unless I just forgot to do it, which is also kind of like a fair possibility. Oh, here we go. Okay, so the head loss so more often than not, you're going to get a question that doesn't allow you to ignore losses because at the end of the day, it's not year 12 physics anymore. So sad. So, head loss is broken down into the biggest loss is due to friction, right? The only case that you can assume no friction loss is when like your pipe is so like insanely long that it kind of becomes like negligible. Sorry, not the friction loss, the exit and entry loss. So when your pipe is hella long, then that little bit of energy that you've lost at the beginning and that little bit of energy that you've lost at the end, it's like negligible, right? But I'm talking a really long pipe, like here to, I don't know, Melbourne or something like that. Like a really long pipe. So, friction, the formula for that, HF times length over diameter. So length as in length of the pipe, diameter as in diameter of the pipe, times U squared on 2G. Okay? So, that's friction loss. Head loss, so it's friction plus usually entry or exit. And in that case, that would be, so let's say HE would be K times U squared on 2G. Now, K, I can't remember the exact values for entry and exit. One of them is like 0.5 and one of them is 1. I can't really remember which one is which, but your teacher will tell you. So, if you've got a question that wants you to include head loss, then you're tacking on to the end of your equation plus HL. But HL is H of friction plus H of entry plus H of exit plus H of any janky movement, okay? So the only funky one is the friction. That has its own special formula, this one. But entry, exit, janky movement would all be K U squared on 2G, and they'll give you K. They'll be like on the diagram. So let's say you've got your pipe and it goes like janky, like I said, like this. They'll be like K2 is 0.3 or something like that. Like they'll label it on the diagram, but you just got to remember to include it. So head loss, all of the potential losses. So it becomes a bit of a fat question, can't lie, but the actual math is not that deep. It's not too bad. Yes, so that pumps turbines. That's kind of it. So, what I was saying before was the Bernoulli, you're going to think, why bother learning the Bernoulli equation if I then have to do this? If you're really good at the Bernoulli equation, this is so much easier for you because then you're just adding on all the losses, right? So it's worth your while to sit down and practice all of them without the head loss. So you get good at remembering like, oh, the velocity is the same because the diameter is the same. Oh, the pressure is 0 because it was exposed to the atmosphere. Like get really good at that so that when you tackle this extra crap on top, you're not learning the entire concept in one go. It just makes your life so much easier. That's low-key all I had prepared. Let me take a look at Farhan's notes to see if there's anything extra I should add. The one topic I very much did not include because I hated it was dimensional analysis. So you're totally on your own for that one. That topic sucks shit, okay? So weird, so useless, so unnecessary. Yeah, that's kind of it. Is that all okay? Cool. It's a good course, guys. Trust. It's a good course.
You guys all take it.
It's also worth, side note, this sounds weird, but going to the library and borrowing the textbook and practicing the shit out of the questions from the textbook, because as a person that did that, like 2 of the questions they just take from the textbook. So you can borrow it from the library for free, and it's like pretty good practice. And it has like worked examples and stuff. Oh, I have it with me. I actually haven't returned it since week 1. So that's the textbook there. There's like 5 copies in the library, and it's got like all like worked examples and stuff. So I highly recommend borrowing that one. Once I return it, and probably pay like a $20 late fee. Thank you.
That's true.
That was way too short.
quite informative.
That's good.
If you guys ever need any like questions or help, just like ask me.
The slides. She's getting you were recording this one.
Pardon?
You were recording this.
Yeah.
Where's the recording of that?
Leo, he did.
The recording for this.
Yeah.
So the recording will be uploaded to YouTube.
Oh.
Yep. So I'll be on the Surfsuck channel.